Welcome back. Today we're going to start talking about differentiation, basic differentiation rules. But we're going to start by introducing the relationship between the slope of a function and its derivative. And all a derivative is really just basically the slope evaluated at a point. Normally, if I asked you to calculate the slope of a function, you pick 2 points on the graph. I'd probably have to ask you where you want to calculate the slope at. You pick a couple points and calculate the slope, figure out what the intercept was, and so on. There are some basic rules that we'll encounter along the way as we talk about derivatives: the power rule, the sum rule, chain rule, product and quotient rules, exponential rules, and so on. And so let's get started. We're going to use an example here, which will be the porosity-depth relationship, which we have up here, the relationship between porosity and depth beneath the surface. We have an exponential decay relationship. This could be in kilometers, and this is our porosity. And we want to know what the derivative is, or what the slope is. We want to be able to calculate it at any arbitrary point. But for starters, let's take a look at the gradient, the porosity gradient between 1 and 2 kilometers. And then we'll consider, well, okay, if we were to, we're kind of interested in what the gradient is at 1.5 kilometers. What would happen if we move these 2 points closer together? So up here we have the slope calculated between 1 kilometer and 2 kilometers. We get a slope of minus. It's a negative. It's a dropping off as we increase in depth. 0.099. We'd say, well, okay, 0.1. Change in porosity with 1 kilometer depth. If we did that same computation now at 1.4 and 1.6 kilometers, we'd get a different result. But again, what we're doing is we're just calculating the slope, delta phi, delta z. This is our delta phi over here, measured off this axis, and our delta z over here. So we're just taking the ratio of those two values. Now, if we did it at these 2 points, we got point at 1.4, point at 1.6. Then we get a slope of minus 0.0982. And so we're just looking at the slope of this line. You can see they're very close to each other. So actually this rather crude form of estimating what the gradient is at 1.5 kilometers works pretty well. And the derivative of the slope of the tangent line at 1.5 kilometers is actually minus 0.0981, so very close to the value we get when we evaluated these 2 points right here. So that's a fairly laborious procedure that we have to go through in order to calculate the slope. We have to get the coordinates for these 2 points, calculate our delta phi, delta z, and so on. What we'd like to be able to do is to get a function which represents the derivative of this, so we don't have to go through kind of the mapping of the slopes. So we have a point here, which is the slope at 0.5 kilometers. We've got a point here at 1.5 kilometers. This is the slope. You can notice that the slopes are negative. They're a scaled version of the original porosity. We can see the original porosity function dropping off, but starting up here at 0.4, we're starting down here somewhere around a little bit less than minus 0.3. We continue calculating the slopes, and we get a pretty good general idea of what the slopes are going to look like. They're converging asymptotically on zero porosity as depth increases, or zero gradient. if we draw a line through there, we visually we can see what the derivative is going to look like. So it's converging on 0. These are the gradients. They're negative. They keep getting smaller and smaller. These lines keep getting these slopes at a point keep getting closer and closer to 0. So we get deeper and deeper in the section. So if we look at what we're doing over here, we've got this delta phi delta z. We're going through the laborious process of calculating out the gradients, and they're negative, and we get these numbers over here. Now, this turns out to be what the derivative is. We'll talk a little bit more about how we get this later on, but if we take the derivative of the porosity depth relation phi 0 e to the minus z over lambda with respect to z, it turns out to be minus, well, we see that we have the original porosity function here, and it's scaled by minus 1 over lambda. And where does that come from? We'll talk about that when we talk about differentiating exponential functions. But here we have the derivative written out, and we've evaluated it at 0.5 kilometer depths, 1.5 kilometer depths. This should be 3 kilometer depths. Sorry about that. And we see that these agree very well, 0.19, 0.19, 0.098, minus 0.1, a little bit of a difference. The difference is getting a little bit larger as we get deeper in the section. But the derivative is exact, and it provides an analytical expression that's easily evaluated. We don't have to go through this process of, okay, this is the porosity and the depth at point X and point Y. We just evaluate this function at this depth, assuming that we know what these constants are, and we get our derivative. We get the gradient. So pretty much for any function, here we have the cosine. We've got a delta y, where y is equal to the cosine of theta, delta theta. And we go through this computation. So cosine theta 2 minus cosine theta 1 over, and we have about a 0.02 delta theta, and we know that it should be equal to 0 at, the slope of the cosine should be equal to 0 at theta equals 0. Go through this computation. You can see it's a laborious process. We go to pi over 4, or 45 degrees, and the slope of the cosine is minus 0.7. At pi over 2, or 90 degrees, it reaches its maximum negative value of minus 1, and so on. So a laborious process. And if we plot these up, we've got the slope up here. Remember, that's just a line drawn tangent to the function at this particular point. And keep sketching in these points, and until we kind of begin to see what the derivative is going to look like. And as we go through this process, point by point by point, we can see that the derivative of the cosine looks like the negative of the sine. We know that the sine would go up like this. And so the derivative has a shape that looks like the negative of the sine, and that in fact is what the derivative is. So it's a lot easier just to go in and plug in a value of theta, calculate the slope at an arbitrary point, and if we know how to get this, if we know what it is, then our job becomes a lot easier. And that's what this idea of studying derivatives and how to get them is all about, because we like to know what gradients are, we like to know what the rates of change of functions are, we like to know how one function varies with respect to one dependent variable, varies with respect to another dependent variable. So that's pretty much what we're doing when we are evaluating the derivative. So here we are, another function, y is equal to x squared. We go through this more laborious process. We evaluate the slope at these different points on the function, and we can see that they are trending along along a straight line there. You know, what is this? You know, how do we get this straight line from this function? How do we figure out what the derivative is? Well, I think that you can see that the slope, if we look at our delta y over delta x, is going to be equal to 2. It's a straight line. The intercept is 0. So the derivative is just going to be equal to 2x. So how do we get that? How do we get that? Something else to think about when you're working with derivatives, you know, now in the future with pretty much any kind of function, is that if you have a constant, if you're summing a constant in to that, you know, if there's a constant term in the dependent variable that you're differentiating, when you differentiate that, you know, remember that that constant term represents a flat line, that its derivative is just equal to 0. So a slope corresponds to the derivative. We can calculate the slopes, you know, we've shown. There's a little bit of error, there's a little bit of difference there, isn't there? We've kind of noticed that when we calculated the slope of the exponential decay function here. Here we've got it calculated out in a little bit more detail. The calculation of slopes has been carried out at a 0.1 kilometer, 100 meter interval from 0 to 10 kilometers. We can see the slope is the red line. Again, it's a scaled version. We can see that our phi 0 here must have been 0.5. And it's scaled. You know, all the slopes are negative, as they should be. If we look at the slopes of this curve, they're negative, and they get smaller and smaller, and they converge. The gradient of the porosity converges on 0. It's a scaled version of the original porosity function. But we can see very little daylight between the derivative and the slope. In fact, that error is consistently 2.5% as we go from 0 to 10 kilometers. That's calculating at a 0.1 kilometer interval. So a fairly small error. But it's much more easy to go through this computational process here if we know what the derivative is. And that's what we're doing when we talk about differential calculus. We're studying how, you know, the mechanical process of determining what the derivative of a function, you know, in this case the exponential decay function, actually turns out to be analytically. So we'll be talking about more differentiation rules as we go along. The next time we'll be talking about the power rule. So until next time, see you on the next video. We'll talk about the power rule.